Yeah, it's working. Thank you for the introduction. So now I'm going to talk about some high-performance consensus protocol. And it's good that we have a talk in the evening because we already touched so many topics, starting with the consensus workshop in the morning about multi-proposal protocols and data availability layers just by early. So what I'm going to talk about, some high-performance BFT protocol in which we integrate some data availability solution, and we also make use the magic of erasure codes to amortize the communication complexity of the whole protocol. Okay, let's start from the general picture. So we consider a typical blockchain scenario where we have clients. They are connected to some validators. They create and submit transactions. And the goal of validators is to sequence, execute transactions, and then send the result of the execution back to the client. And for this talk, we will mostly focus at the moment when the transaction first came to one of the validators and when it gets sequenced in the log by all correct validators. So we are focusing on so-called like ordering task or just consensus task. We consider a Byzantine environment, meaning that some nodes, some validators can be faulty. It means that they can deviate from the behavior arbitrarily, but there is at least quorum of correct nodes. And typically, to many protocols, we look at partially synchronous model. It means that until some moment called global stabilization time, the communication is completely asynchronous, and then this moment is unknown, and after that moment, the communication finally gets synchronous with the predicted delay delta, which is usually a protocol parameter that is used for timeouts. So in the solutions that I'll describe, we will use direct acyclic graph as a communication and logical layer. And basically, we will come to the decision how to sequence all the transactions using one data structure. So, and typically, inside one block, we have several fields, like which round, who is the author of this block, who are the ancestors, who are parents, probably transactions, probably transaction commitments, and we also have signature. So, and here we have several rules on how we construct the DAG. The first rule is basically we try to create a block in each round, and all honest, all correct nodes should create the block in each round. The second rule is that we shouldn't progress ahead of the network, so we need to wait until a quorum of the network already created blocks from the previous round. This means that we have kind of like cordial progression of the whole DAG. We just respect the network. Otherwise, our blocks will not be considered as valid. And lastly, as I said, we will use only the DAG structure for sequencing. And typical for this area, and it's like in spirit of PBFT style protocols, we choose some nodes to be leaders in certain rounds. And these nodes will create blocks. And if you'll find in the DAG a special structure, then we'll say, okay, this leader block is committed. And then I can slice the DAG using this leader block, using all the references. And I can then sequence all the transactions in all these slices that I'll have after cutting the DAG. So, and what's important is that we wait not only for the quorum of blocks from the previous round, but we also wait for the leader block in the previous round, because in our DAG interpretation, we'll use some kind of like virtual votes, some references included in the block, and we need to have these links to the leader from the previous round. One thing that I probably didn't mention is that we want to have a really low latency protocol, and all the validators will be connected with each other. So meaning that we need only one hop just to send a block from one validator to another validator. That means that our network is not just huge, it's of size, say, 100, maybe up to 200. But it's the system just that optimized for low latency. Okay, and next thing is that there are typically just two types of DAGs that are considered in the literature. The first one is like certified DAGs, where each block can be seen as certificate, meaning that before adding such a block into your local DAG, you need to ensure that this block is already well disseminated. And the block creator is basically responsible for providing such a certificate. So first it sends the block, then collect the signatures, and then send back the certificate. So here usually in production, we use consistent broadcast. For theory, you need to use reliable broadcast for block dissemination. But as you can see, it requires much more rounds to construct such a certificate. So usually you need 2-3 rounds to construct a certificate, and that results in higher latency compared to so-called uncertified DAGs. In uncertified DAGs, we basically receive a block from some peer, and we check that we have all the parents, all the ancestors of this block, and we know all the causal history of this block. And after that, we optimistically include such a block in our local DAG. This allows to progress the DAG construction much faster, and eventually it results in lower end-to-end latency, because if we just receive a transaction at some point, then this transaction is included in some block on much shorter time in uncertified DAGs rather than certified DAGs. But what is the caveat of uncertified DAGs? Definitely, we could have equivocation blocks. So for instance, here, the node D created 2 blocks and sent one block to validator A and one block to validator C. And since we include blocks optimistically, both blocks will survive in the DAG. We will need to maybe exclude equivocations when we'll just do sequencing. But in general, this method allows for equivocations. But this is not the only problem. The other one is related just to how we broadcast the blocks. In theory, if you want to prove things, then let's look from the perspective of node of validator A on top. It creates a new block, A6, and now just thinking, okay, what shall I send to validator D? Because validator D, from my current perspective, validator D doesn't know block B5 and C5. And then, to ensure just liveness of the protocol, I need to send these potentially missing blocks to validator D. This is okay, but the problem, of course, is in the communication complexity. So you need to send basically every block between every pair of peers. It's too much expensive for us. The practical solution, so if you look at the mysticity protocol, what was suggested is just, okay, let's just stream or broadcast our own blocks. And if the peer doesn't know some of the ancestors, then it should pull it and we will send them. It looks fine. I mean, on the practical terms, it looks fine. From theoretical perspective, you cannot do this. And here is the issue, which happens not only in theory, but it also actually happens quite often in practice. Suppose that we have a slow validator, say here validator B is slow, and it creates its own chain of blocks. They all valid, they all satisfy like the rules, but for some reason the slow validator just got connected only to one peer. And then it sent this chain of blocks to only one peer who created a block in the next round and referenced this hidden chain, orange chain of blocks. And then this validator A is just thinking, okay, if I use pool-based dissemination, then I'm gonna send only my own block to all others. And this block is sent to validator C and D. But let's look just what happens from the perspective of validator C. It just receives this block from guy A, and it understands, okay, there is a missing ancestor, I need to request it. Then I need to request another ancestor, and this pooling strategy takes a lot of time to collect all the missing ancestors. And that's exactly the issue that we're gonna solve. So on one hand, we don't like quadratic complexity. On the other hand, we don't like pool-based dissemination. So one thing is good probably in theory, another thing is good probably in practice, and we want to achieve linear amortized communication complexity, and we want to use push-based dissemination. And here just two ideas that we use here. The first one is we want to decouple the block structure, and we want to have separately transaction data and the block header. So it's usually how it's done in many protocols, because in Mysticity, transaction data was included, it was part of the blocks. And it's helpful because then pushing the block headers is much simpler. They are not of great size. It's probably of size 3 kilobytes or something. And the headers are sufficient to drive the consensus. It's sufficient just to continue progress of the DAG to sequence blocks, sequence transactions. And if, say, we don't have some data, then we can pull it. But what's important here, since we separate these two things, transactions from the block header, we need to ensure that the data was well disseminated. And since we could have up to F faulty nodes, we need to have some kind of acknowledgements from the nodes that the data is locally available to them, and then we can at least pull the data from them. So it means that in the block header, we need to also include acknowledgements. This is like a new field that we need to have. The second idea, just because the first idea is enough to make pushing strategy in practice, but the second idea is needed to improve, to amortize the communication complexity. So now what we are going to do, we are going to encode transaction data using, say, Ritz-Lemon codes. So let's say that we have information, so we have transaction data, we divide it into information shards, and it coded into parity shards. So altogether we have n shards, and basically each validator is then responsible for its own shard, for broadcasting its own shard. So when you are a block creator, then you definitely need to share what you are aware of, full transaction data to every other validator. But if you are not a block creator, then you're responsible for only one shard. And of course, you need to have some kind of proof just to show that it's part of the full encoded code word. Then when you just want to have access to the data, then you either receive this full data from the block creator, or you can decode from any F+1 shards. Here, for sequencing, already we need to have two F+1 nodes acknowledging this data is available, because previously I told that it's sufficient to have F+1, but for this solution we have two F+1 acknowledgements, because F nodes could lie, and we have at least F+1 nodes. They will share the shards, and we can decode the data from F+1 shards. That's the reason. And let's look on how we broadcast in this case. So let's say, again, we just created a block, A6. What we are going to broadcast together with our block, we're going to send the block headers, and we also will include the shard corresponding to our index. So in this case, we'll send the shards for blocks P5 and C5 if we have the data locally available. So let's take a look then how when we're gonna sequence transaction data. We're gonna sequence it in the following case. So let's say that we have this block C1 with some transaction data inside. Then this block is broadcasted to other validators, and in the next round, or maybe a little bit later, validators just say, okay, hey, I know this data from this block, and I acknowledge it. So it will be part of the block header. And it means that I'm gonna send my encoded shard to everybody else, or maybe I can send it later if you'll put from me. The next step, we have again leader block. So the leader block needs to observe at least two F+1 acknowledgements. And the rest is basically what we have in uncertified DAG approach, in cordial miners, in Mr. SETI. We have some virtual votes, which is part of the block headers, and we treat some blocks as certificates for the leader. So in total, we need to have like 5 rounds to sequence the transaction data in block C1. And in case like C behaves dishonestly and does not provide the data to the validator B, then B, if it knows, it sees that from the DAG structure that transaction from the block C1 should be sequenced, then it should have at least 2 shards sent by correct validators. That means that validator B, in this case, will be able to reconstruct the data. Okay, and let's go finally to the results that we have. So let's look first at this picture. And here we have a geo-distributed network. We have 100 validators, 10 regions, and half of kilobyte transactions. So first, you can see certified DAG, Starfish. It's like the state-of-the-art protocol, which provides the lowest latency across certified DAGs. And you can see that, as I said before, when we look at the end-to-end latency, then certified DAGs, they grow slowly, and the transaction is getting included in the block much slowly than in uncertified DAGs. We also have here a red curve, and it basically corresponds to the protocol called cordial miners, the first in this class, and it uses really a push-based encoded dissemination strategy. And it's very expensive. You can see that basically we can hit the bandwidth limit immediately, even at 10K transactions per second. It's too much expensive. So again, on the x-axis, we have the throughput. For y-axis, we have end-to-end latency. And if you look at the 2 other protocols, so green one is Starfish that I presented, and the blue one is just the best in the class for especially low-load Mr. SETI, which uses pool-based strategy. As I said, for Starfish, we need so-called acknowledgement steps that the nodes say, okay, I have this data, and this is the reason why for low load we have better performance for Mr. SETI. But interestingly enough, for large load, we have better performance for Starfish. And primarily the reason for this is because in such a network, when we deal with large transaction data, we don't necessarily have this triangle inequality. And the data sent by validator A to B and C can be achieved by C faster as a block header. When B receives a block from A, then B can send the block header much faster than the block sent by A arrives to C. But the reason why we just were thinking about this protocol is from practical perspective, because it gives much more robustness against some misbehavior or when some validators have bad connection. And for instance, if we have just one Byzantine validator and we have some specific Byzantine behavior, then we can increase the end-to-end latency for mysticity protocol, whereas it's quite stable for any number of validators in Starfish. And finally, just if you look at all the recent protocols that's proposed in the last, say, 4 years, we can just see here then Starfish achieves linear amortized communication complexity, and the end-to-end latency is like significantly lower than all other protocols can achieve in this class, which has linear amortized communication complexity. Okay, that's the summary of my talk. So today I just talked about uncertified DAG-based protocol. It has quite low latency. It uses push-based block dissemination, and we incorporate Rich-Solomon encoding in this dissemination process. It achieves the lowest latency in the class of DAG-based protocols with linear amortized communication complexity, and it has much better robustness against some Byzantine attacks than other uncertified DAG protocols. Yeah, thank you.